Okay. Are we sitting comfortably? Can everybody hear me? Okay, awesome. Hi. Hi. I'm Jonathan. It's good to be here. Yeah, I am. I promise I'm Jonathan. It's nice to have made it to YAPCNA. I've done a bunch of YAPCs, some in Europe, some in Asia, some in Russia. Finally, I made it over to YAPCNA. So it's good to be here. Thank you. So who am I? Well, I'm this guy. I do various stuff on Perl 6. So, you know, if you were in Patrick's talk this morning, then he gave a very comprehensive list of the stuff that I'd done, or forgotten that I'd done, or tried to suppress that I'd done. I actually have a day job too. You might not believe this, but as well as doing all of this Perl stuff, I actually do stuff like, you know, teach software architecture and advanced C# courses. So I kind of do, you know, a load of stuff over in the .NET world as well. It's actually good being involved in multiple language communities. It's actually a really good thing. And one of the reasons it's really cool is because you can sort of spot interesting things they do and say, oh, I like that, I'm going to steal that. And one of the ones that I saw recently was a thing on .NET called RX, the Reactive Extensions. So what are the Reactive Extensions? Well, they realized that if you happen to know something about category theory, which I kind of don't, but it doesn't matter anyway, then if you actually take the enumerator pattern or the iterator pattern and you figure out what is the mathematical dual, you get the observer pattern. And that means that we can go and define all the familiar sort of enumerator combinators that we use every single day on observables as well. Now at this point you're either thinking, that's awesome, or, huh? So let me explain. It's easy. Okay, so let me show you first the enumerator case. And we can turn to Perl 6 for this. Let's talk about lazy lists. So lazy lists are really great because they let you talk about infinite things without filling up all of your memory. So what we can do here is we can take a range that goes from 1 up to infinity. And I'm actually just using binding for all of this rather than assignment, because binding is guaranteed not to go and try and be eager at any point in the operation. And what I can do is I can take this infinite list of numbers and I can grep out all the primes. So that's star dot syntax, makes a little closure. And then we can map them so the output comes out something like, you know, number 1 and then the first prime number, and number 2, the second prime number, and so on. And again, that's an infinite list. Okay, all these lists are infinitely long. But I haven't actually done any work yet. What I do down here is I say, I want to get the first 10 things in this list. So that little hat and the 10 makes a range. It's the same as 0 dot dot 10. 9. Thank you. It was good beer last night. So what actually happens then is at that point we go off and do the work. And there's a nice little bit of syntax called the feed syntax as well. So what's going on with this feed syntax? This is this nice, oops, that's the pointy one, there we go. That nice little pipe thing there basically says take this 1 to inf and then shove it into the grep, and whatever the grep gives, shove that into the map. And then we just do the 10 thing again. So if you think about what happens when this is evaluated. So here we have it. And this guy in the end is like, hey, map, I need 10 elements. And map is like, grep, I need 10 things to map. And grep is like, oh, range, you know how to make values, don't you? And the range says, oh yeah, I do, here you have some. So it's pull-based. At the end, we're sort of begging for these values. We're saying, give me them, give me them. So we always block on getting the previous thing. We're pulling them through this set of things. So that's very familiar, and I'm glad I've told you about that because we need that for the hard stuff we're going to do later. But the question is, what if we wanted to push instead? What if we're doing something more asynchronous? And we want to push data instead of pull it through pipelines like this. Well, That's what an observable is. So let's write a little observable role. There's not much to it. We declare an attribute up here, an array of things that are observing us, things that when something happens to us, we will invoke. And then we can subscribe something to observe it. We have an unsubscribe, that's kind of boring. And we have a publish method, and all it does is whenever something happens, which is represented by this object, we take all the things that are observing it, and we go over the observers, and we call handle on all of them. So basically it's publish subscribe, okay? Every time somebody registers or subscribes, they get to know all the things that happen. Now it turns out that if we go and start writing stuff like this, okay, so I just did a really simple thing. It takes a file handle, it just sits getting lines from the file handle and publishing each line. This is good enough to be an observable. So what I can then do is I can start defining all those familiar things like grep and map and first. Here's grep. What does grep do? Well, here's a little grep subscriber. Notice how I can use lexical classes. I don't need to leak this anywhere else. So the grep subscriber just takes hold of the matcher, the thing that we're going to grep against. And when it gets some input, when something gets pushed into it, it says, does it match? And if it does, it publishes it out to all of the things that are observing it. So then I can start writing code where I take this sort of source of events or items of data, and whenever one comes in, I can just use this nice pipe syntax, because I've done all these overloads, and I can grep for all of the things coming through, and I can shove them into some other observable, and I'm putting in nums, and then I can take that, and I can grep out all the prime ones, and I can stick a call at the end, which says, oh, that's a prime. Or I can take them, I can map them, and I can keep count using a state variable. So I can see when I get up to 100 different things. And then I say, I just want the first one. So what it actually does is it unsubscribes after it's got one. And then we just call this thing at the end. And what's going on is it looks very much like the code you would write if you had a thing at the end that was pulling the values through. But instead, what's actually happening is things are getting done at the top, and they're getting pushed. So if we run this, here I have it. Okay, that's a prime, and I guess that's a prime. I'm pretty sure that isn't. It would be very odd if it was. Okay, and then notice that we actually hit the more than 100 point. But it's unsubscribed now, so if we go and do some more, okay, and there we have it. So, well, that's basically the idea behind this kind of dual idea. And what we've done is we've taken this familiar notion of enumerables, and we've taken this familiar set of operations that we use every day, like grep and map, and we've realized that if we just apply the dual, we can actually use all of these same familiar things working with asynchronous inputs and pushing the data through instead. Well, that's kind of nice. There's no blocking there. That's kind of nice for async. And I sort of looked at this idea, and well, I sketched it out in Perl 6, and I was like, well, okay, I'm done with that one now. But I started thinking, is there anywhere else in Perl 6 that I could actually take this idea of, just turning an operation around, of flipping the inputs and the outputs, and maybe getting something kind of cool out of it? So what about grammars? So the thing is, what a grammar does is it takes in a string, and it spits out a tree. So basically, it's doing text to data structure. Let's take a little example. This is a little grammar for JSON. So what's going on in here is, well, let's just read through it. We have a token top. This is a magical token, which is the start of doing the pass. And then we say, well, JSON at the top level can either be an object or it can be an array. What does an object look like? Well, it looks like curly braces, and between the curly braces, there's a pair list. And a pair list is a pair. We have the star there. That's from regex, familiar syntax. That's 0 or more. And then they can have commas between them, which is what that % comma does. It just says there can be commas that go between each of these pairs. And a pair is a string, a colon, and a value.
Why do we start everything with a null assertion?
Because if you do not, then you do not pass white space here under the current 6-space rules. Yeah, you hadn't used to need that. We maybe don't, but this is safe. Okay?
Code is 1 character shorter.
What's that?
Code is 1 character shorter.
True. Don't think it gets optimized as well, though.
Whose fault is that?
Patrick's. Okay, so an array list is kind of the same. All right, it's a list of things that go between square brackets. So you can sort of see that we're sort of representing the sort of object graph we're going to get out. We're sort of describing the shape of it in this grammar. Now we have these wonderful things called proto-regexes, which are basically like multiple dispatch but for regexes. But instead of actually doing a multiple dispatch, it runs a little automata which goes and figures out which is the best one and which ones are impossible and all of these nice things. So for example, we can actually just say, well, there's true and false, which are actually just true and false. The sim just lets me refer to this bit of text in here. And we might have an object, or we might have an array. So you can see that this is getting recursive. Okay, so we might actually have, an array of array, because an array list is a bunch of values, and a value can be an array or a string, and so forth. And so it goes on, and I don't want to sort of go and dig any further into this one, but hopefully you get the picture of what we're doing. We're describing how to pass a string into a bunch of actually what we call match objects, and they form a tree. Now, that's only so useful. And what makes this more useful is we have these things called actions. And the actions get run after we successfully pass a grammar rule. And what they do is they just take the rule, the match, and they make some kind of Perl data structure. And then they pass it on upwards. So by the time you've gone all the way down the tree passing, and you've worked all your way back up to the top, you now have built up some kind of Perl representation of what you passed. So in that case, it turns into arrays and hashes and so forth. Okay, so here we have a few examples. So number actually just takes the string we passed and use Perl 6's plus operator to nullify it. For true and false, we just make a Perl 6 bool true and bool false. For objects, well, they start from the bottom. Okay, pairs, we actually make a Perl 6 pair. And what you'll notice is that we're able to take whatever the string produced and get the object. And over here, we're able to get the object using the .ast method for whatever the value produced. And when we say make, what we're saying is pass it on up. So down here, when we take the pair, and we actually have a list of them, and we use the hyperdispatch, and we call AST on all of them, what we get is this list of pairs, and then we pass that up, and then object gets the pair list, which is this flat list of pairs, and it just calls hash on it to turn it into a hash.
Question?
Yep.
So .ast here is basically the getter, and make is basically the setter.
Yep, basically. And it sets on $/.
Right.
Yep. Okay, so that's parsing. And you put it all together, And what you can do is write something like from JSON, which makes the actions, it makes the grammar, it passes in the JSON string, it sets the actions, and what comes back is some Perl 6 object which represents that bit of JSON, so we've deserialized it. Okay, so we've been able to do this for ages. We've been able to do this for some years. And that's great. But I wondered, what if? Sometimes it's good to ask what if. After I saw this Jules, I was like, well, what if some grammar actually had a generate method, and we could put in some kind of tree-ish thingy, and we get out a string. That is, we can use the grammar not only to take text and pass it into a data structure, but we can use the grammar to take a data structure and turn it into a load of text. Well, that's a curious concept. So can we do it?
Apparently.
Hey, this could be like the guy who wrote his PhD on 200 ways not to make this chemical. Yeah, we haven't got there yet. Okay, so if we could make this work, okay, just take a really naughty example. My goal is to make the JSON one work, but let's start somewhere easy. If we were to have a grammar that did simple sentences, so you can see here, the sentence has a subject, a verb, an object, and I was to throw in, and actually, what are we going to send in here? Well, it turns out that, match objects aren't actually that practical. In fact, if we had a match object, we'd actually have the string, in which case we're already done. So that would be a bit too easy. But we do have something in Perl 6 which represents a set of positional things and a set of named things, which is just what we want, and that's a capture. And capture literals are written using the backslash, parens, and then we can just put pairs in. So what I can do is I can describe a little tree which has a sentence at the top, and then the subject is this, the verb is this, and the object is this. And in theory, if we take those and we call generate, I hope I get out the string, Petrucci plays guitar. Who knows who John Petrucci is? Really? Gee. He's like the only guitarist I know.
That's this dog.
So, let's try and break this problem down a little bit. What happens when we're passing text? If we take each individual regex construct, one thing you'll realize is that while some of them can only match one particular thing, some of them can actually match in multiple different ways. In fact, quantifiers can match in loads of ways. That's what backtracking is. So what I'm going to do to sort of be able to model this sort of operation and think about how to twist it around is to think of every single regex construct as if it produces a potentially empty, lazy list of all of the ways that it can match. So for example, if I have AB, sequential or, ABC, and I feed it the string ABCDEF, it can either match in the way AB or ABC. It would prefer this one, but it can do this one if it has to. So essentially, every construct in my regex can be viewed as essentially producing a lazy list of ways that it can match. So in generation, we'll have to worry about that. We'll have to sort of flip that around. But there's another thing we're going to have to worry about, which is backing off. So what happens when we're passing is if we try this path, subject, verb, object, and it turns out that when we get to verb, the thing that it actually says is, it rained. There's no object. So what we do is we say, oops, this path does not work.
Isn't really a subject either.
And we go over here. It's a thingy. What do you call them? Platonic things? I don't know. I'm not a linguist.
I think it's called a placeholder subject.
Yeah, something like that. Well, there's plenty of other examples.
A good example is setup.
Why didn't I think of that one? Okay, so if we're generating, we're going to have to worry about this too. Okay, we're going to go down paths trying to generate stuff based on stuff that is in the tree, and then we'll get so far, and we'll be like, there's no object in this tree. So we'll have to fail that path, and we'll have to go back and try this one instead. So we're going to have to, when we generate, we're actually going to have all of this sort of backtracking-y stuff going on, or these sort of paths not working out and having to fail. So we need to sort of do all of those bits as well. So it's not quite trivial, but it still seems kind of doable. So let's dig into the meat of the problem. So what happens when you feed a Perl 6 compiler a grammar? Well, it passes it, using a grammar appropriately enough. And what it does is it turns it into an abstract syntax tree. So each thing, say the literals, the quantifiers, the rule calls, they all turn into nodes in some representation of the regex. So what if we steal that? What if we find a way to steal those trees? That means we don't have to pass the regexes. We can just let the Perl 6 compiler pass them, steal the AST, and then use it to do the generation. So the question is, how the heck do you do that? Well, the compiler is written in Perl 6, and it's in, okay, when we're passing, it sort of is in the dynamic scope. So what happens if we write an export sub, and this is something that gets run at the point we do a use of a module, and we pass in %lang, which is the current set of languages that we're passing. And then what we do is we take the current action methods.
Ooh.
Exactly. And we mix a role into them. And this is kind of cool because we're mixing a Perl 6 role into like the compiler.
And it's lexically scoped.
And it's lexically scoped. So we do, yeah, so if you do a use of this, any grammars that are inside will have the AST stolen and do the right thing, and anything outside won't. It's like this language was really well designed or something. So then what we do is we just take an override of regexdef. We go and look at the Perl 6 grammar and realize that the correct thing to steal is this thing called nibble. Om nom 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 regex. We do call same to do whatever we would have done before. And then what I've done is I've also just written the extra little meta object, which gives me a place to save these pieces of AST. Okay, so what I do is I get the current package. This is the current grammar that we're passing, that we're inside of. And I get the current declarand name, that is the current regex. And these are not sort of objects that just refer to the things, these are the actual real objects. Okay, so as we're passing your Perl 6 programs, we're really making the grammar meta object, and we're really making regex objects. And when we get to the end, if you want to make bytecode, we just serialize a lot. But we can get hold of them as we're passing. So what we do is we just steal these bits of ASTs, and we save them under the rule name. Well, that was naughty.
Yes.
But we didn't have to write any C. Yeah, and it's portable. It'll work on Rakudo on JVM eventually as well. Okay, so let's do something less naughty but still kind of cool. So what we'll do now is we kind of realize that we need that generate method. So what I'm going to do is I'm actually just going to take the default meta object for grammars. This is the object that says how grammars work. And it turns out that a really cute idiom for sort of tweaking the way certain keywords work is we go into the module export how, and if you write a class called grammar, then this is how you can actually say how grammars are going to work differently. Cutely, if you wanted to say how classes work differently, you'd write class. And it's the fact that it's inside of this export how module that makes it all work out.
Can you do class export how :grammar?
Yes, I think so. You'd have to put a my on. No, you wouldn't, but you should. Okay, So what we do is we just actually override new type, we delegate to it, and then we sneak in this generative role. Okay, so every grammar gets a generative role mixed in by default. And then I have some boring code in here, which I won't show you, which is just a hash which maps names to the ASTs that we captured for each of the rules. So what about the generative role? Well, this is where we start to get into the generation. So let's take it piece by piece. There's only one method in this role. It's called generate. It takes the thing that we're going to use to generate from. It takes the rule to start generating at, which defaults to top. And there's a :g, which means do I want all of the possible matches or all the possible generations in this case, or just one. And then what I do is I go and I look up the generator for the rule of that name, which is an object that knows how to generate based on a certain piece of AST. I call generate, I pass in the grammar object itself, I pass in the match, I bind it to an array, and then all I do is I say, well, if we need all of them, then we'll just sit in a gather and just generate and take each one. Otherwise, we'll just get the first one. Okay, and we're stringifying it at the end as well. So that's really just the entry point to it. So what about the generation? Well, basically we sort of do a little bit of compilation in here. But it's not the scary kind of compilation, it's just making closures and putting them in trees. So what I do, the first time we call generate, we don't have a generator method yet. Okay, that's just an attribute that's going to hold some code. And this is an attribute that contains the AST. So what we do is we just use the defined OR. And if we don't have one of these, we go off and compile it based on this AST. And all compile does is it's this big switch statement on the type of regex node that we're currently compiling. So it might be a quantifier, it might be just concatenating several pieces of regex together, it might be a literal. And what we'll do is we'll make a little closure for each of these, which we're going to be able to invoke at the end, and we're going to put all of these together. So just to show you a couple of examples, this is the one for literal. So a literal has a string that we're going to emit. And we just say, when we have a literal node, we make this closure. It takes two arguments. It completely ignores them. One is the grammar, one is the match, but it doesn't need them in this case. And we always should return a lazy list. But in this case, we don't need to care about the lazy because there's just one thing in it, okay, which is the string. So this sort of icky aside, basically all we're doing is we're saying, well, the way that you generate the text for a literal is you just give back the literal string. So there's only one possibility there. What about some of the other constructs? Let's talk about sequential alternations. These ones are more fun. So the first thing that we do is we take all of the things in the alternation. Okay, so we might, if you remember, we had the sentence verb, subject verb object, or subject verb. Okay, so the subject verb object is the first thing in this list, and the subject verb would be the second. And we just map them. We call compile for each one of them. So what we get back is an array of closures there in the @generators, which is basically something that can generate each of these things. Then we return something that takes the current grammar, the current match state. It does a gather. So gather take is a very nice little construct for building iterators. You write gather, and basically it runs up until the first take when it needs an item, and gives the item back, and if we need another item, it runs it again until it gets to the next take, and so forth. So what we do is we go through the generators, we invoke each one of them with the grammar and the match, and we take the results. We loop through the results, taking each one, And then there's a special exception type here, which is grammar generative enable. And what this means is the path that we went down ran out of ways to produce results for us. So if that happens, we'll just try the next alternation.
You can't just use an empty list for that?
Apparently not. There was a reason why not, which boils down to the fact that if you can't generate at all, you need to flow that all the way up to the top. And we actually throw one here, okay? If we run out of ways that we can possibly generate, we say at this point, okay, that's it, we're out of ways. We could potentially use an empty list to the end of the list to indicate that as well. It turned out cleaner with the exception. Okay, so basically, you do things like this, but worse, for concatenation, alternation, quantifiers, subrule calls, and anchors. And anchors are a real mess when you're doing this stuff, because you sort of have to go looking either side of them. But you're trying to generate the string out, and it was horrible. You should see the code. Anyway, what we get by the time we've defined all of that is something where we take some JSON tiny grammar, and we call generate. And if you look, we pass it in an object which has a pair list, which has pairs, and here's the string for the name. Here is the value sim string, okay, and there's another one. And out the bottom pops this. Well, there we have it.
Where does the white space come from?
The white space comes because every time it hits WS, at the moment it cheats and says, oh, a space is always safe. So it actually gets multiple of them in there. We could be cleverer, but I wasn't feeling clever enough.
Yeah, well, that actually is indicating that most of those angle question marks were unnecessary in the original grammar, because the rule calling them already ate the white space.
Yes, apparently so. Damn, I wish I was that smart. Okay, so this is almost good. However, we're not quite there yet. And the reason we're not quite there yet is because, if you remember, we had these really nice action methods. We had these things where instead of you getting this big AST back, this big match tree back, you got a real object back. So what are the equivalent to those? Well, if we think about it, actions get run on the way back up. Okay, so on the way down the tree we pass, decide where we're going, and as we come back up the tree, we build up that result data structure. So actions run on the way back up. So what we need is something that will go the opposite way around. So we just need to turn it backwards. We need to run something on the way down, and then assemble the string on the way up. Okay, so what we're going to be doing is running whatever we call these things as we go down and try and figure out how we're going to generate the string. And we'll be generating the string and getting the string out at the top. So basically it's just, flipping the sides. So I called these things bactions. And yeah, what you do is you just write methods which correspond to rule names, and what they do is they produce the capture which will be used to generate that kind of rule. So what you see here is if at the top we're passed in some kind of array, then we end up in this multi-candidate like this. And what we do is we say, well, if you have one of these, then you need to take the array path. If you remember, the grammar had a path that we could follow for arrays and for objects. So we say you take the array path, and then what you need to do for the array is you need to take this data structure and dice it. So dice is kind of the opposite of make. We had real fun coming up with a word for this. I was trying to get Carl to help me with this on the plane. And originally I went with break, because you make or break. But then I realized break would confuse every C programmer ever. So we didn't do that one. And then it's kind of like, well, what are equivalents of break? And there's like burst, destroy, devastate. And then there's like, well, no, what you're doing is sort of taking it apart. So, like deconstruct, and oh, it went on forever. What? Slice. Yeah.
We discussed slice.
We discussed slice. It punned badly.
By at least various languages.
Yeah, so we ended up with dice, which is, well, what you do with meat, I guess, or something.
For instance,
So what this does is it basically...
Roll.
What's that?
There are things with 20 sides on them that you roll to generate random numbers.
No, the verb dice. Subs are verbs. Okay, so, apart from when you noun them. So what we're doing here is we are just taking that array and just saying, I want to shove that down, and when we actually try to call and generate an array for the text, then what we should do is we should run, well, the array bit of code. And we did the same for object, and basically this is the way that objects work. Okay, we take the hash, and we dice it into its pairs for pair list. Pair list gets the pairs, and it maps them and dices every one of them, and then puts that array of pair. Pair is quantified, so it calls pair for each individual one of them, which then says, well, we'll have the string being this, and the value we'll need to dice. Okay, and then the value, it's actually smart enough to sort of go and call that, and just like we use protos, we can actually use multiple dispatch on this side. On the data structure, which works out kind of nicely. So this is the way we say, oh, this is a number. So you put it all together, and what we can do is we can feed this little data structure in here, which is something very much like what JSON tiny's pass with the actions would give us. We feed in the backtions, and we get out the JSON. Mission accomplished. So, I write it a module. It's still quite experimental. But basically, to give a grammar these capabilities, you just do use grammar generative in the scope where the grammar is, and it gives you this stuff. Any guesses how many lines of code this one took?
400 in total?
300.
In total.
299.
I don't actually know the answer, but I'll have to go and have a look.
401.
It is... Wow. Wait, I already pushed this to GitHub.
Yeah.
Who was cheating? Okay.
Your friend.
I
That's wireless connection.
yeah. So the surprise was actually that the one for concat was really good fun. The reason the one for concat was really good fun is because basically things being next to each other can all backtrack in all the combinations if you want to generate all the ways. So what you actually end up doing is recursing with this collect routine, which uses the signature syntax to pull out the first item and leave the rest, and then it recurses, and you're sort of recursively setting up this chain of gathers, and then hopefully they all take to the right place. And it actually works, which is kind of cute.
How much memory did you have?
My machine at home's got like 16 gigs, but this actually runs, by the way. So the demo script is just the grammar, okay, and the actions, the backtions even. Okay, so here they all are.
Fractions?
And there's the little line at the bottom. Okay, oh, there it is. Okay, so there we have it. Okay, so thank you very much. That's how you turn grammars around. Any questions?
When I read the description for this talk, what I thought you were going to be doing was adding probability annotations to a Perl 6 grammar, and then using it, and then turning it into a stochastic context-free grammar and using it to randomly generate input for fuzz testing purposes.
That would be a lot of fun as well, and I think that's kind of why the G option is there, so that you can actually get it to spit out lots of random things. So I think there's going to be a whole load of fuzzing applications for this as well down the line. So that's an area of future exploration, but yes, it would be cool. Okay. Yeah?
Were you able to deal with white space that you threw with, or I guess it would have to be.
Can you deal with white space?
Is it going to put back the pod comments?
No. Yeah, I mean, it puts in white space in the places where it thinks it, needs it according to the WS rule. But, it doesn't preserve it as such. Any more? I can't actually see to the back of the room. So. Is there someone there? Okay.
Seems to be right.
For error reporting to have the line numbers attached.
Sorry?
I often wanted to have for error reporting the line numbers attached.
Okay, the question was you want to have the line numbers attached. The line numbers of what exactly?
No, for error reporting. So if you got an error in the pass stage,
It's unparsing.
yeah, but it's the same.
So we want to take the errors as input and
No, we produce the error.
Oh, you mean when you're passing, you'd like a way to get hold of the current line number?
Yes.
Um,
In the
is that spec'd somewhere?
yes, I'm missing.
Okay. Well,
You do position of where you matched so far, and then you count new numbers.
well, yeah, you can always get the current position. I mean, if you fail, you can always get the position to where you'd matched up to. So you can then count the lines from there. That's just plus whatever dot lines. One thing that we do when we're actually passing Perl 6 programs is we keep a high watermark, which is the furthest we passed before we ever failed. Maybe we should expose that in a more general way. Maybe. Okay, anything else? Okay, then I thank you for enduring this crazy. Thank you very much.